Every time you ask a chatbot a question or generate a digital image, a physical reservoir loses water. We experience artificial intelligence as a frictionless, instantaneous digital tool, but that software relies on a massive extraction of physical resources, draining millions of gallons from local environments. At the micro level, the numbers seem harmless. A single text query to a generative AI model consumes roughly 1/5 of a teaspoon of water. But when you multiply that microscopic transaction by the billions of daily queries processed globally across platforms, the aggregate consumption accelerates. A comprehensive study by researchers at Cornell University modeled the trajectory of this infrastructure. They project that by 2030, the global computing boom will drain up to 1.125 billion cubic meters of water per year. That equals the annual household water usage of 10 million Americans. This drain on the watershed is an inescapable hardware bottleneck, tied to the physical reality of thermodynamics. Scaling up intelligence currently requires risking global water security. Through the previous decade of the cloud computing era, traditional enterprise server racks operated predictably. They consumed between 6 and 15 kilowatts of power per rack. Managing the heat generated by these servers was relatively simple, requiring massive computer room air conditioning units pushing cold air through optimized aisles. The shift to generative AI changed the requirements for data center cooling. Training a large language model, an artificial intelligence system trained on vast amounts of text to understand and generate human language, requires running arrays of tens of thousands of graphics processing units continuously for months. A GPU is a specialized circuit designed to rapidly process the complex mathematics required for machine learning. As technology conglomerates race toward artificial general intelligence, they are packing these processors into dense clusters. Generational leaps in silicon architecture are drawing concentrated amounts of electricity. The pursuit of smarter algorithms is bound by the limits of heat dissipation. To keep the servers from melting, the industry has been forced into a resource-heavy evolution in facility design. We can trace this thermal crisis to a metric called thermal design power, or TDP. TDP is the maximum amount of heat generated by a computer chip that the cooling system is required to dissipate. NVIDIA's Hopper generation of chips maxed out at about 700 watts. The subsequent Blackwell architecture pushed that to 1,200 watts per individual chip. The next generation hardware, NVIDIA's Vera Rubin platform, shatters existing engineering standards. When 72 Rubin GPUs are clustered into a flagship rack-scale system, the total power density explodes, packing over 150 kilowatts of heat into the same physical footprint as the old 15-kilowatt enterprise rack. At 150 kilowatts, air is an ineffective conductor of heat. Pushing cold air over the chips is insufficient for these thermal loads. The viable engineering solution is direct liquid cooling. Facilities must pump massive flow rates of warm water, between 15 and 25 degrees Celsius, through cold plates attached directly to the silicon. The liquid absorbs the heat, preventing thermal throttling and equipment destruction. While liquid captures the heat efficiently inside the server chassis, that thermal energy does not disappear. It must be rejected from the building. The heated liquid cycles through a coolant distribution unit, which transfers the thermal load out to the facility's exhaust systems. Because of the scale required to train trillion-parameter models, hyperscalers rely on open-loop evaporative cooling towers to reject this heat. The hot water is exposed to outside air, vaporizing millions of gallons of local freshwater into the atmosphere and removing it from the local watershed. By transitioning from air-cooled racks to liquid-cooled silicon, the industry successfully protected its processors, but it transferred the thermal burden of the internet onto local municipal utility grids. This heavy reliance on water evaporation is driven by carbon accounting. Technology conglomerates have committed to net zero emissions targets, which requires them to optimize their power usage effectiveness. PUE is a ratio measuring how efficiently a data center uses electricity, comparing total facility power to the power actually reaching the computing equipment. A more efficient PUE means lower carbon emissions. The best way to lower the electrical cost of cooling is relying on evaporative water systems. Lowering the carbon footprint degrades the facility's water usage effectiveness, or WUE, the ratio of water used for cooling against electricity delivered to the hardware. The water vaporized on site is only a fraction of the total consumption. The industry also commands an indirect footprint through embedded water. Thermoelectric power plants require enormous volumes of fresh water to create steam for their turbines and to cool their reactor systems. This diagram shows the scale of the disparity. A 2024 report from the Lawrence Berkeley National Laboratory estimated that while U.S. data centers consumed 17 billion gallons of water directly, they consumed an additional 211 billion gallons indirectly through the electricity grids powering their processors. Major technology firms exclude this embedded water metric from their corporate sustainability headlines. Internal strategy documents have revealed executives reporting only their smaller, primary water usage, specifically citing the reputational risk of publicizing their total secondary consumption. This creates a severe, zero-sum environmental trade-off. To report energy efficiency and meet global climate goals, corporations treat local municipal water basins as a subsidy, masking the true energetic cost of their data centers. To counter mounting public scrutiny, major tech firms pledge to become net water positive by 2030. They promise to replenish more water than they consume, investing millions into sustainability credits by funding projects like municipal leak reduction or wetland restoration. Unlike carbon emissions, which diffuse globally, water is an intensely localized physical resource. Funding agricultural conservation in a remote location does not refill a specific drought-stricken aquifer being actively drained by a nearby server farm. Knowing that heavy water usage triggers public backlash, the industry utilizes land acquisition strategies to secure resources before local communities can react. Hyperscalers hunt for cheap land and electricity, securing power and water rights long before construction begins. They achieve this through non-disclosure agreements and obscure limited liability shell companies. By pushing projects through zoning boards under aliases like Jasmine Development or Project Blue, corporations bypass municipal environmental impact studies until construction is well underway. Corporate sustainability reporting allows firms to legally market global environmental stewardship while physically extracting local resources through opaque legal structures. The friction between silicon expansion and human survival is fracturing communities. In Arizona, a state enduring extreme heat and a rapidly drying Colorado River system, local leaders approved the region as the second largest hub for data centers in the United States, hosting over 150 facilities. Residents bear the financial burden of these demands. Upgrading municipal infrastructure to support massive cooling loads forces utility boards to pass the cost onto homeowners, resulting in residential water bills that jump from hundreds to thousands of dollars, despite no change in personal usage. Desperate for power, the AI arms race is pushing into the global south. In Uruguay, Alphabet attempted to construct a hyperscale facility in a tax-free zone, requiring up to 2 million gallons of potable water per day directly from the public drinking system. This industrial extraction collided with a catastrophic physical reality. Uruguay was suffering its worst drought in 74 years. With the primary reservoir drying up, desperate authorities were forced to blend saline water from an estuary into the public drinking supply. The contrast was severe. Citizens were forced to consume saline, unsafe tap water, or manually haul expensive bottled alternatives, while a foreign corporation planned to evaporate millions of liters of the country's dwindling freshwater for cloud processing. From rural Michigan to South America, the localized externalities of the artificial intelligence boom are overwhelmingly borne by working-class and farming communities, acting as involuntary subsidies for trillion-dollar corporate valuations. Preventing ecological failure requires an architectural shift. Hyperscale operators must abandon open-loop evaporative cooling models that permanently extract from municipal water supplies. Engineers are pivoting towards closed-loop liquid systems. These designs recirculate the treated fluid continuously, minimizing evaporation and isolating the data center's thermal management from the public potable water supply. A promising alternative is two-phase immersion cooling. In this architecture, entire server components are submerged directly into a non-conductive engineered refrigerant. As the silicon generates heat, the fluid boils and vaporizes, rising to a condenser where it cools back into a liquid and falls back into the bath. This creates a continuous, sealed, zero-waste loop, capable of handling the thermal density of modern GPU clusters. Decoupling AI compute from the global water supply has become a requirement for industry survival and the deployment of next-generation hardware. Voluntary corporate mandates have not slowed the crisis. Instead, they have triggered a wave of legislative pushback, forcing the industry to redesign its physical footprint. At the federal level, United States senators have launched an investigation into the agreements between tech giants and utility companies, challenging the framework that passes the infrastructure costs of AI expansion onto everyday consumers. Local legislatures are erecting defensive guardrails. Proposed laws in California aim to enforce conservation measures, while municipalities in Arizona have amended their zoning codes to prohibit the use of potable municipal water for data center cooling. The public requires systemic digital transparency. Just as we mandate Energy Star ratings on appliances, we need transparent environmental footprints for the software tools we use daily. The ecological cost of generating an image or querying a model cannot remain hidden behind corporate non-disclosure agreements. Exposing the physical reality of these systems is the first step to ensuring the pursuit of digital intelligence does not engineer a thirsty, uninhabitable future.